Good morning, Physics 30s. Mr. Thompson here. All right, we're looking at the speed of light, page 73 of the workbook. Okay, we got two early methods to determine the speed of light. One's Galileo's lantern. It says the first serious attempt to determine the speed of light was done by Galileo, 1564 to 1642. He and his assistant stood on two distant hilltops with shuttered lanterns. Galileo opened his lantern first, and when his assistant saw the flash of light, he was to immediately open his lantern. Galileo then used his pulse to determine the time from the initial opening of the shutter to when he saw his assistant's flash of light. Finally, knowing the distance between the hills, he would calculate the speed of light. Oh, geez. However, it turned out that light traveled so fast that the reaction times were way too slow to accurately measure the time. In fact, light would have taken about 70 microseconds to travel the distance, which would have been impossible even with digital timers. All right, Ole Romer and Huygens. All right, says here Olaus Romer, a Danish astronomer, observed the motions of the moons around Jupiter. Although other scientists had already determined their periods of revolution, Romer wanted to determine the exact moment that one of the moons would experience an eclipse, when Jupiter would be in front of the moon. He noticed that as Earth got closer to Jupiter, the times of the eclipse came earlier and earlier than expected. As Earth moved further away from Jupiter, the times came later and later. Romer concluded that as the Earth got further away, light had to travel further to reach the Earth, and thus the eclipse was seen later. This is illustrated in the diagram below. And so light had to travel across the diameter of Earth's orbit. That's why it took that much longer. He was able to calculate that when Earth was furthest from Jupiter, it took 22 minutes, or 1,320 seconds, longer than when Earth was closest. He concluded that this was the approximate time the light took to travel across the diameter of Earth's orbit around the Sun. A few years later, the Dutch mathematician and scientist Christian Huygens calculated the diameter of Earth's orbit, and using Romer's data, calculated the speed of light as follows. All right, you got a number of 2.3 times 10 to the 8. Interestingly, the speed they determined was so fast, most scientists of the day rejected it. It wasn't accepted until after their death. All right, let's take a look at the more modern method here. So we're looking at Michelson. In 1905, the American scientist Albert Michelson used a rotating mirror to make a very accurate measurement of the speed of light. His device is shown below. All right, so you got essentially a light source reflecting off a rotating octagonal mirror. It's a fixed mirror, reflects back and to the observer, which would be through a telescope. Obviously a very large distance here, because light does travel quite fast. When the mirror is rotated at the minimum frequency, about 32,000 RPM, to see continuous light, the time for 1/8 of a revolution is the time for light to travel to the fixed mirror and back. So the mirror rotates through 1/8 of a rotation to be in the same orientation so that light can reflect predictably into that telescope. The equation looks like this. Its speed of light is d over t, which is 2 times the distance between the fixed mirror here and the rotating mirror, divided by 1/8 t, where t is the period of revolution. All right, so it says here, note, for an n-sided mirror, we use this formula. Speed of light is d over t, which is 2d over 1/8, instead of 1/8, 1 over n times t. Today we use lasers to calculate the speed of light through a vacuum. The currently accepted value is, this. In Physics 30, we just use 3.00 times 10 to the 8 meters per second. All right, let's get to some practice problems. Just hold on for a second. I'll be right back.